Welcome to a lesson with Dr. Powell. Let's continue the last example that we had where we were looking at this function and we computed its first derivative and we computed its second derivative as a matrix right here at a point x, y, z. Okay, now where can minimas and maximas occur? Because that's what we're going to be looking at. They can occur where the function is momentarily stationary, meaning that its linear transformation, which describes how much rise we're going to give it, is equal to 0 at some point. So the output of f is instantaneously stationary. Okay, so we look where the derivative transformation is equal to 0. So it's the same like the zero matrix as a linear transformation, same way that we've thought about this before. For instance, like in a calculation here, we have 2xy plus z x squared x. That's the first derivative that we computed. When is this all equal to 0? Well, we're going to concentrate on this point as an example. I mean, this is not the only point that makes it 0, but we're going to use this as an example for testing. So 0, 1, 0. Okay, so let's look back over here and think, okay, what if we have a point where it's like a critical point where the first derivative matrix is the 0 matrix, all right? So I'll call P that point. Point P could be the 0, 1, 0 that we were just discussing. So let's suppose this this point is in the input. So this is a picture of the input of F, okay, wherever it may be. Here in this particular example, it's x, y, z, so it's in space, it's in free space. And let's suppose that we have a vector. We can make it small as we like. So that emanates from that point coming outward. Let's just draw a circle around it and examine around this point, right where that vector touches, and think about what's happened. Okay, so along this vector v, right? Okay, at the end of that vector v, the derivative of the function at the particular input value, which is this point plus the vector v, okay, is actually equal to the change of the derivative vector from that point to that point, because at this point, the derivative vector is 0, all right? Or the derivative matrix is 0. And then over here, but this matrix can be thought of as a vector because it's a row, right? Matrix, just a single row. Okay, so this derivative matrix is 0, but so the change is simply equal to what the derivative matrix is at that point. So that minus 0, of course, is itself. So you can think of it that way. Now, what's the benefit? Because we can know that this change is approximately equal to the second derivative of f with v plugged in. How much has df changed, the first derivative, changed from here to here? What's the rise of the first derivative from here to here? Well, it can be approximated by the second derivative of f with v plugged in. So the value of the derivative right here is approximately the second derivative of f with v plugged into it to tell us, okay, that's approximately what the first derivative is going to be. Okay, now let's take a look at that for a minute. Now let's suppose we want to approximate what the change of the function is, but starting at this new point here at the end of that vector v and going another length of vector v. All right, so this idea won't work from P, but it would work from here, from this point right here. So we're going to approximate how much the function changes from here to here. And how much would that be? Well, that's going to be approximately equal to using the value of the derivative at that point P plus V with V plugged in. Okay. Now, okay, with V plugged in. All right. Now, wait a minute. We can actually approximate this guy right here with this. That's what we were just talking about. Like this can be approximated with that as a matrix. So wait a minute. Okay, so we have like, okay, now wait a minute. So this outputs a matrix, and that matrix is then multiplied to V. So so V is multiplied to this matrix to give us a matrix, and that matrix multiplied to V to give us a value. And that value, it would be nice if, as we're heading away from point P, if these change of S were all positive, And if we made these circles as small as we could to kind of drive this idea as close as we can to the point P, um, if change of f was always positive as we're looking outward from P in any direction, then um, that would mean that this point P would definitely be like a minimum because f will be growing. Um, the output of f will be going up as we head away from P. So that's kind of one way of thinking about um, how to ensure that a point P is a minimum. Okay, but we actually have a really nice way of looking at this. Um, this is kind of a little description. I'll give another video, I'll give a technical argument um, that shows this um, more specifically. But for now, for intuition, this is really enough. This is really all we need to think about if we want change of f to be, if we want f to be increasing past p, so p would be a minimum. So let's take a look at this for a minute. All right, so we know the second derivative is equal to this, and we have two inputs, right? We have this v and this v. Okay, this guy right here, the second derivative with v plugged in, we could think of it like this. Think of v as being a column vector. But then wait a minute, we have this other v to plug in to the derivative. Remember, this this is under the column interpretation, right? So we input a vector v. Let's take a look at that for a minute. So we input a vector v and we output a column. So the derivative, the change of the derivative, or the derivative itself is being expressed as a column. So, but we need a dot product with that. Well, we need to change the input of the derivative then to be a row and put it on the other side to get that dot product. This is just representation of it. So we put this v over here. So we have vt v. So this is like so this matrix right here is going to have like two different vector inputs. It's going to have one on this side and it's going to have one on that side. Okay. Um, let's see. It's going to have one on both sides, and we're inputting the same vector v to signify kind of what we were doing here in this case with the v and the v. Okay. So so it's going to look like this. We can call it a bilinear form. And it's always, in this case, the second derivative is actually always a symmetric bilinear form. If our function is nice to begin with, fairly smooth, this is basically if it has polynomial type approximations to the function nearby, this will always be true. We'll just, for now, we'll take that fact for granted, but it's going to give us a symmetric bilinear form here. Now, if okay, so we've had a video that actually discussed these forms right here. If we want this value, this output value, which represents a change of f on a certain interval, remember, it's actually from here to here, approximately, that is. So from the end of one v to the end of the other v. So kind of like at this point, not this point, but right over here. So if we're going to be approximating it over there, if we want that to always be positive, the output, because this is going to output one value, because this is a row, right? So output of one, and this is a column, so input of one. So it's going to be a 1 by 1 as we come out. And we want just a number. If we want that number to always be positive, then it's called and this is a bilinear form, it's symmetric, then that's called positive definite. And one way to get to make sure we have a positive definite matrix is to check all the eigenvalues to see if they're all positive. Then it would be a minimum. If they're all negative though, then it would be negative definite, and then this would be a maximum, a minimum. That's kind of what we do. So it really reduces the case to look at the second derivative and then just see if all the eigenvalues are positive or a negative or a mix. If it's a mix, then it's neither a max or min. If it's all positive, it's a minimum. If it's all negative, it's a maximum. That's pretty much it. But just to give some intuition to what's going on, that's why we discussed those ideas preceding this. All right, so let's actually work through this. Let's let x be a scalar representing the matrix right here. So this x is not the x previous in the definition of the function. It's a different one. Oftentimes people use a different variable like lambda. I'm just sticking with x. Just realize that what x refers to here in this case. So we compute the characteristic polynomial by saying like x down the diagonal minus the matrix, and we end up getting this. Now, how do we test if all the eigenvalues are positive or negative, or maybe some are even complex? I mean, look at the roots of this thing. Well, just remember, this is a symmetric matrix, and all the roots of a symmetric matrix are real. So that actually enables us to be able to use Descartes' rule of signs to do this. And to be able to look at this. So there's looking at another video that I will have in the playlist. And that one will actually show you show you what Descartes' rule of signs is and how it works. But pretty much what we're doing here is we're looking at the signs of this guy as we go this way. So the signs of the coefficients. So positive, minus, minus. Notice there's one sign change as I'm reading this way, which means that there's at most one positive root, or you can go even number less, but there's exactly one, is what it means, because we can't go an even number less. So there's only one positive root, but wait a minute, that means all the other ones have to be negative. So there's a mix. So this is neither a max or min in this instance. In the next video, I'll actually give you an example of, I'll give you an example of one that actually does work, where we actually get a minimum or a maximum. Thanks for watching.